Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be exploring the properties of logarithmic expressions. In particular, we're going to go over what the properties are for simplifying logarithms in an attempt to both condense and expand logarithmic expressions. We're going to see ways of simplifying them down to a single expression and ways of kind of desimplifying them and expanding them out into larger expressions. This work is going to help us when it comes to solving logarithmic equations in particular. So first, let's go ahead and let's actually learn about the different properties. So before we begin, we need to define what we're working with here. Let the variables or the terms b, x, and y be positive real numbers. So right away, b, x, and y are positive real numbers. They're any number on the number line, and they're greater than 0. But you should note to yourself that b here is not a 1. Do not let b be 1, okay? Also, sometimes you'll work with the term p. That's just a standard real number, okay? So pretty much everything here is a real number, except b, x, and y have to be greater than 0. And by the way, b isn't a 1. Then you have these 7 properties. The first one says, if you're taking the log of b, log base b of 1, it's 0. If you have log base b of b, it's a 1. If you have log base b and your argument is b to the p power, you just end up with the exponent p. If you took the value b and you raised it to the exponent of, and that exponent, by the way, is a logarithm. So take b, and the exponent that you're going to put it to is log base b of x. Then all that you get out is the argument x. Additionally, if you're taking the logarithm of two values multiplied together, so x and y are being multiplied together here, then you can add the logarithms of each one separately. Additionally, if you're dividing, you can subtract the logarithms of each one separately. Now, if you take the logarithm of any value to an exponent, you can rewrite that as that exponent times the logarithm. Now, these 7 properties here we're going to use when simplifying logarithmic expressions, condensing them down, as well as expanding them into larger expressions. There is a rationale and a reason for why we have all of these properties. I'd like to take some time to work through each of these and kind of explain where they're coming from. Let's start with number 1. Log base b of 1 is equal to 0. Log base b of 1 is equal to 0. Let's reason this out for ourselves. Remember, when you work with logarithms, it's helpful to rewrite them as exponential expressions. So here I'm going to say the base is a b. Remember, the exponent on b is what the logarithm equals, so that's a 0, and the argument goes right here. So is this true? B to the 0 power is 1. Well, yeah, that's true. That's true for pretty much any number. It's not true for 0 to the 0 power. Remember, that's something that's a little different. Sometimes we would say that's undefined. But keep in mind, we said that b here is a real number that's greater than 0. So we're not even worried about this case, okay? So hopefully this first rule makes sense to us. It should be fairly obvious. Let's try the next one. The next property said that log base b of the argument b is equal to 1. Again, this is fairly obvious once we convert it into the exponential form. We have the base value, we have the exponent, and we have where the argument goes. This is true. B to the first power is always b, okay? Nothing to worry about there. And this works for any real number, in particular any positive real number. Now let's move on to the next one. This property might seem a little odd to us at first, but again, once you put it into exponential form, it's fairly simple. Go ahead and try this for yourself. Pause the video for a minute and try rewriting this as an exponential form. Well, hopefully you were able to rewrite this into an exponential equation. Remember that the base is still the base number that we have when we're taking the exponent. The exponent is what the logarithm equals. And then the exponential will equal the argument, b to the p. Is that true? Yes, of course that's true. That's an obvious identity right there. So this will work. If you had, for example, log 5 of 5 to the third power, that's a 3 right there, it's just going to equal 3. Because what this is saying, say I didn't know what this equals. I'm just going to put question mark. Well, if I rewrote this as an exponential, what I'm saying is 5 to that unknown power is equal to 5 to the third. Oh, gee, I wonder what that unknown power is. It's just 3. Again, hopefully this problem is making sense to you. Let's go ahead and take a look at one now that actually is in an exponential form. Here we can see that we actually have an exponential equation. We have a base value raised to some exponent equaling a value. Well, let's see, why does this work? If I were to rewrite this logarithmically, maybe it will help kind of shed some light on what's going on here. Now remember, if I wanted to take the logarithm of this, I would take the logarithm of base what? Well, here, the base is still b. That's the base number. And I want to know what it equals, x. So that's the argument, and that's the base. Now the logarithm will always spit out what the exponent is. Well, here, the exponent is just log b of x. And what do you know? We get an identity. We get a true statement here. So if I were to say something like 5 to the log base 5 of 3 power, this is going to equal 3. The exponent with the logarithm is going to cancel out here, and all we're left with is 3. Again, the reason for that would be, if I were to take this from an exponential to a logarithm, I would say the base number was 5. The argument is a 3, and it's going to equal the exponent. Well, here I happen to know that the exponent is this value itself. So that's why it works. This is really what's producing an identity. Now let's take a look at the 3 properties that help us to expand logarithmic expressions. Now, for this property, we are going to need to define a couple things first. Let's go ahead, I'm going to change colors here. I'm going to start with the right-hand side. I'm going to work with both of these terms individually. So let's start with log base b of x. Log base b of x, that's just going to equal some quantity for me, right? So let me make that a quantity. Let me pick something like, let me pick some term. Let me pick alpha. I'll do alpha there. And let me change colors here. I'll go green for this next quantity. And I can say that log base b of the value y, that's just going to give me another quantity. And I'm going to say that quantity is, let's say that this quantity equals epsilon. Epsilon is like a round e, or kind of like a reversed 3. So I've just gone and said each of these quantities is equal to some value, right? Like each of these are going to produce some number. And I've defined what those quantities are, alpha and epsilon. Now, what I'd like to do for a minute here is I'd like to also rewrite these logarithmic expressions in terms of exponentials. For example, let's take log base b of x equaling alpha. This is the same thing as saying b to the alpha power equals x. And then for log base b y equaling epsilon, this is the same thing as saying b to the epsilon power equals y. All right, this shouldn't be anything new to us. We've just gone and we've defined what each of these logarithms is going to be represented as, what it's going to equal, and then we've rewritten them to also be able to work with exponential forms. Okay, that's fine. Well, where do we go from here? Well, let's go back into this equation, and now let's look at the left-hand side. The left-hand side said that we want to take log base b of x times y. Well, I could go ahead and do that, but remember, I've gone and I've defined what x and what y are in terms of epsilon and alpha. So what I can do now is I'd like to go ahead and sub these values in. So let's go ahead and rewrite this expression. I'm going to try to use as much space as I can here, but let's rewrite what x is equal to. We said that x is equal to b to the alpha power. So instead of saying x times y, I'm going to say b to the alpha power. And instead of y, I said y is equal to b to the epsilon power. So I'm going to write b to the epsilon power for y. So these two statements are exactly the same because I have what x and y are equal to. They're exactly the same thing. Nothing wrong with this. Let's now go ahead and use the multiplication of like bases property. Remember, when we are multiplying the same base value, we can add their exponents. So log base b, b to the alpha power times b to the epsilon power is the same thing as b to the alpha plus epsilon power. Well, let's take a look here. Log base b of b to the alpha plus epsilon power, didn't we have a property before? Didn't we say when you have base b of b to a power, you just have what that power equals? So let's go and take a look here. Log base b of b is equal to alpha plus epsilon. And you know what, let me go ahead and color code these. I remember alpha, we were working in red here. And then epsilon, we were working in green. So all I did here was show that log base b of x times y is equal to alpha plus epsilon. Well, how does that help us show this whole statement right here? Well, it's actually quite simple. Take one more look. You know what alpha and what epsilon are equal to. So let's resub those in. Before, we did a substitution for x and for y. Now let's do a substitution for alpha and epsilon. Alpha, we said, is equal to log base b of x. And epsilon, we said that is equal to log base b of y. And we're adding these together, so we can say that log base b of x times y actually, when we simplify everything, gets us log base b of x plus log base b of y. Here's a little proof-based explanation of why this is working, okay? Do you have to know this? No, you don't, okay? I'm not particular about people memorizing and be able to derive why certain properties work, but it's helpful to see kind of how the inner workings of our explanations are coming, where they're coming from. It's helpful to know that we're not just making this up as we go along. There's a reasoning for all of that. Let's use a similar argument, but this time for x divided by y and subtraction. Now in this property, we have the similar understanding, except instead of working with x times y, we have x divided by y. And instead of having the logarithms being the sum of the two, we're going to subtract the two logarithms together. Well, we can use a pretty almost identical argument to this, where we start by taking what log base b of x is equal to, and I'm going to say that's equal to alpha, okay? I don't know what b and what the log base b of x is equal to, right? But I know it's got to equal something. It's going to be some number. So I just say that's alpha, and I say log base b of y is equal to epsilon. Again, I don't need to know specifically what they equal. I just need to have some representation of it. So then I can say, all right, instead of having the logarithmic forms, let's convert it to exponential. I now know what x and y are equal to in terms of b alpha and epsilon here, okay? All that this is doing is giving me ways of visually representing things, okay? This is like doing a substitution, like when we used to do systems of equations. Now, go ahead, pause the video, and try to see if you can yourself figure out how log base b of x divided by y can get you all the way down to log base b of x minus log base b of y. All right, well, hopefully you used a similar argument to before, noting first that we know what x and y are. You can see I color-coded things here to be a little more helpful to us. Instead of working with x and y, I subbed in what I said they're equal to, okay? By just simply knowing the fact that the log base b of x must equal a number and the log base b of y must equal a number, I was able to rewrite what x and y could be. So I just did a substitution. So instead of dealing with x and y, we're now dealing with b to the alpha power and b to the epsilon power. Okay? By the way, alpha and epsilon, those are just Greek letters. I figured, well, I'm kind of running out of letters I could use from the alphabet that we typically use, so I just switched to Greek. Anyways, I know that if I am dividing like bases here, we have the property for the division of like bases that says you can subtract their exponents. Well, just like before, we have that property that says log base b of b to some power. These just cancel out and you're left with whatever the exponents are. So, since log base b and b canceled out, we're left with alpha minus epsilon. Well, again, you know what those equal. They're just simply log base b of x and log base b of y. Again, this is a simple way of showing that log base b of xy can turn into log base b of x minus log base b of y. Let's take a look at one more property, and this one involves the exponential in the argument. Now in this property, we can see that we're taking a logarithm, and in particular, we're taking a logarithm of an exponential expression. And this says when you take a logarithm of an exponential, you can bring that exponent out front. And this is what you end up with. That exponent times the logarithm, and you have the argument as if there was no exponent in there. Now, why is this? This is a little weird, but it should be somewhat similar to when we have log base b of b to the p power. We said, oh, you would just get p. These would cancel out. And we showed why that works. This time, what we want to show is why is this working? Because b and x are not the same number here. They could be the same number, but we already have a property for that, right? Here, what we want to show is what happens when they're not the same number. Now, there's a few different ways of proving this or showing why this is working. I'm going to do a way that really focuses on the right-hand side. Again, when I'm trying to show why this is working, I'm trying to take one of these sides and turn it into the other. I'm trying to show that the left-hand side can turn into the right-hand side or vice versa. For this example, I'm going to start with the right-hand side, because when you start with the right-hand side, it's pretty easy to see how you can turn into the left. So let's start with p times log base b of x. Keep in mind, log base b of x, that's just a number, right? It's going to be some number. And when I say p times all of this, that just means take log base b of x and add on that many more logarithms. For example, if I said 3 times log base 5 of 13, whatever, I'm just making something up. This is saying take log base 5 of 13 and add it 3 times. Now my handwriting is a little messy here, but you can see that I have 3 logarithms being added together. If it was times 4, that would mean add it 4 times. Times 5, that would mean add it 5 times. That's what multiplication is, repeated addition. So when I say p times the logarithm, I want to add p of these logarithms. Well, I don't know what p is, right? So I'm just going to say pretend like I've added it p times. P could be 1, 2, 3, 4, 5, 200, whatever. Well, I have already shown that when you add all the logarithms together, that's the same as multiplying their arguments together. So I can say, instead of adding all these logarithms together, I can say that's the same thing as multiplying all of their arguments together. Well, all these arguments are x's, right? And how many x's are there? Well, there were as many x's as there were logarithms. And wait a minute, there were p logarithms, right? However many there were here was p, we called it. Well, however many x's are here is also p. So I can say that this is really log base b of x to the p power. What I've done here is shown that by multiplication, I could represent this as repeated addition. There's p log base b of x's. Whatever p is, that's how many you got. And then, using a previous property, we were able to multiply all of the arguments together. Well, how many arguments are being multiplied together? Well, p of them. So that's why we were able to take x to the p power. And thus we showed we started on one side of the equation and got to the other side, okay? This is how we're able to show that this property works. Again, you don't need to know this off the top of your head or need to be able to fully recall this. It's just helpful to know where these things are coming from and how you're able to see how the logic is working from step to step. What properties are we using to go from one step to the other to show how these two quantities or these two values are really equal to each other? Okay, what I'd like us to do right now is actually go ahead and practice using these properties. We see why they're working, but let's go ahead and actually start applying them. What I'd like you to do is pause the video and answer these 7 questions by using the 7 properties we've just explored, okay? Try to see if you're feeling comfortable working with the properties. If you're still not, you could always rewrite all of these as exponentials. And you might want to do that to check your answer, but let's see if we can start applying these properties together, okay? Well, hopefully these properties are making sense to you and you can see how to start applying them. You'll notice that really in each of these, I'm not really needing to show any work here other than knowing what the properties are, okay? Now, some of these, you'll notice that I went ahead and rewrote them. For example, log 6 of 36, well, I know that 36 is 6 squared. So by rewriting that, I could use this property to show us that it's equal to 2. Again, I didn't have to do that. I could have just used the fact of turning this into an exponential. Log base 6 of 36 is equaling some exponent. Well, 6 to what exponent gets me 36? 2. All right, so that one's not that bad. Again, you can always still solve these using exponentials. But when it comes to solving logarithmic equations, we're going to need to know the properties that are working here. Notice that log base 3 of 3 to the log base 3 of 5 gave me just 5. Keep in mind that these need to be the same number. If they're different numbers, the property doesn't work here. Log base 4 of 8, I rewrote 8 to be 4 times 2. So I could then say, oh, well, that's just log 4 of 4 plus log 4 of 2. And you could keep simplifying from here, but I just want us to first right now see how the properties are working. Similarly, for number 6, I subtracted the argument 6 and 5 by taking log 5 of, x and 5, by taking log 5 of x and subtracting log 5 of 5. And then, for the very last one, again, these numbers are different, so I can't use the property from before. Instead, I have to move the exponent out front to be 4 times log base 2 of 3. Now what we're going to do is utilize these properties to take a logarithmic expression and expand it out into the sum and difference of multiple logarithmic expressions. First up, let's take a look at the process for how to do this. It's recommended that we first identify the argument of the logarithmic expression. So using this practice problem right here, we can identify the argument, and I'll put it as a side note here as AB over C. That whole thing is the argument. If there is an exponent, so if there is an exponent for the entire argument, which includes radicals, remember radicals are exponents, apply the power property, meaning that's where you take the exponent that would be outside here and you'd bring it out front. Okay, that's the power property. If the argument is a rational expression, so this is set and we don't need to do this because there's no exponent here. If the argument is a rational expression, a fraction, hey, that's us. Apply the quotient property to separate the numerator and the denominator. That means we are going to take log base 5 of AB and subtract log base 5 of C. Okay, we had the property that said if you have a division in the argument, that's the same thing as subtracting the numerator as a logarithm and the denominator. So we've separated that, so this step is set. If the argument can be written as a product, if you have two things multiplied together in your argument, use the product property. Separate them using addition. So let's look at the arguments here. We have a C. Well, that can't be written as anything other than C and 1, so that doesn't help us. But here we have A times B. That is the product of two factors. So let's rewrite this as log 5 of A plus log 5 of B. And then we still have minus log 5 of C. What we've done here is we used the property that said if you're dividing, you can subtract, and then if you're multiplying, you can add them together. And then we can say simplifying individual logarithms by applying the remaining properties. Well, there's nothing else that simplifies here, right? They have no exponents other than a 1, so we're good there. There's nothing like 5, log 5 of 5. They're all just letters. So this is our final answer. This is how we've gone and expanded the logarithm. Now, this might seem a little odd. This kind of seems counterintuitive to simplifying, but this will be helpful when we actually go and start solving logarithmic equations. So it's got to kind of be a little odd for right now, but once we start solving the equations, then it will make sense why we're doing this. So here we've gone and just use those really three properties. Let's take a look at those properties. The properties were essentially these three, okay? This was the power property. This was the quotient property. And this is the product property, okay? So really what we're doing is we're using these three properties and then any of these other ones, but mostly these three, to break the logarithm apart. What I'd like us to do now is take a look at some practice problems and let's try to expand this logarithmic expression so that way we could rewrite this as a sum or difference of multiple logarithms. So first up, here's what we'll need to do. We always need to first identify the argument. Make sure you know what you're working with. Here the argument is x squared y over z cubed. Okay, is there an exponent out front? If there was, I can bring that down. So there's no exponent here for the entire argument, okay? So I don't have anything to bring out front. Next, let's rewrite this using the division property, okay? Because, hey, it's a fraction. Before I do anything, I better separate the numerator and the denominator. So let's say that this is equal to log base 2 of the numerator, x squared y, minus log base 2 of the denominator, z cubed, okay? So we've separated numerator and denominator. Now I can get at each individual variable. What I'm seeing right here for the first one is that I have an x squared times a y. That's a product. So let me separate each variable here using addition. I can say this is log 2 of x squared plus log base 2 of y. And then we still have minus log base 2 of z cubed, okay? What this has done now is it's separated each individual variable. Now, I should say to myself, could I go any further, okay? I've used the product and the quotient properties to really separate this so I have each variable as an argument. But can I simplify them even more? Can I simplify these arguments further? Well, hopefully you're saying yes for a couple of these. For example, we have log base 2 of x squared. Well, we had that property that said you can pull an exponent in the argument out front. So I will have 2 log base 2 of x. Log base 2 of y doesn't simplify, that can't break down. But here we have a minus, I can pull the 3 out front. Log base 2 of, that's a z by the way, that's not a 2 there. That's base 2 and that's argument is a z. So this is our final answer. Here's how we've gone and expanded the logarithm, okay? Again, you know you're done when you've separated all of the variables, check, 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 and they don't have any exponents left in them, you've brought those out front, and there's nothing that can break down any further. And I mean by that, like, you don't have something like log base 2 of 2, right? Something that can obviously, we have a property that simplifies that. So we're good. What I'd like you to do now is pause the video and take a look at this practice problem. Again, it's similar to before. What I want you to do is try to work through these steps and reason out to yourself why you're going about doing this, and then we'll come back and check our work. All right, well, hopefully this is starting to make some sense to you. But the first thing that we need to do here, besides identifying the argument, which is 4x cubed over y squared, I better rewrite that 2 a little better. We can say that, okay, is there an exponent here? Well, no, there's not an exponent on the entire thing. Really, I have an x cubed, a 4, and a y squared. Those are all kind of separate individual things, right? Separate variables, separate numbers. I want to separate all of them. okay? I want to work with each thing one at a time. So before I can get at each thing individually, I better split up the fraction. I better split up the numerator, so we have log 4 of 4x cubed, and the denominator, log 4 of y squared. And when we separate them, we have to subtract their logarithms. Now again, notice that that numerator has multiple things being multiplied together. So I can separate that to be log 4, let me rewrite that, log 4 of 4 plus log base 4 of x cubed. And then we still have the minus log base 4 of y squared. So our first rationale was, well, if I want to eventually get at each of these things individually, each of these variables and each of these numbers, I better separate the numerator and the denominator. Then, well, I have a 4 and an x cubed. I want them separate, so I better pull those apart. Now we can go and say, well, let's keep simplifying. See if there's any way that you can keep breaking these down using any properties that we know of. Well, here we have log base 4 of 4. What was that property where you take the log and the base and the argument are the same thing? Well, this was just a 1. Then, notice that my argument here still has an exponent in it, so I can bring that out front, 3 times log 4 of x, minus, and then I also have an exponent here, so I'll bring that out front, 2 log 4 of y. Now these logarithms with the variables don't simplify any further, but this would be the final answer. This is my way of expanding out the logarithmic expression as much as as much as I possibly could. We no longer have exponents in there. There's no more products or quotients, and there's nothing really property-wise that simplifies down for us. So we're good. Now let's take a look at these problems. Only thing different here is I've started including radical expressions in some of the numerator and denominators. So again, start by identifying what your argument is. Root 2x over 4. That's a square root of 2x, by the way. What I'd like you to do is pause the video and try these two problems out. You know what their arguments are. This time, you just have to work with radicals. And remember, what are radicals? What way do you have of thinking of them in terms of logarithms and exponents? See if that helps you out, okay? And then we'll come back and take a look at our answers. All right, well, hopefully you're able to see what the solutions are going to be for these two logarithmic expressions. Let's start with taking a look at really both of these. They have the same first step. Notice that both of these start with a fraction. So if I'm going to work with the 2, the x, the 4, the a, the b, or the 25, I have to first separate that fraction. So we've separated them by using subtraction. We've separated the numerator from the denominator in each one. Then when we look at the numerators of each, they're a little different than before. Notice here that the numerator was the square root of 2x. Well, we can rewrite that as being a rational exponent. Instead of saying the square root of 2x, why don't I rewrite this to be 2x to the 1/2 power? Remember, that's what a radical was. It was a rational exponent. So the square root of 2x is the same as 2x to the 1/2 power. Then I took that 1/2 and brought it out front. So taking that, I brought it out front. So we have 1/2 times log base 3 of 2x. Notice right here that I first brought the 1/2 out. I didn't separate the 2x because I'm taking all of 2x to the 1/2 power. okay? It's not just x and it's not just 2. It's all of 2x. So before I can get at either 2 or x, I have to get rid of that exponent on them. I have to get rid of that radical. And this is my way of doing that. I pull the exponent out front. Once it's out front, I then say to myself, okay, now I can work with the 2x. Now I can split it up into the log 2 and the log x. But notice, I want to point out here, notice that I am using parentheses. Notice that this expression right here is in fact in parentheses. Part of that is because I have a half times all of this. Okay? I've taken a half times all of this. So now, when I break down the log 3 of 2x, I still have to multiply that by a half. Okay? Hopefully you're seeing that log of the 2x is this whole expression here. So that's why I have to multiply a half by this entire expression. But we can say this will be the final answer. You could distribute the half if you wanted to, or you can leave it as is. Your call. Now, let's take a look at the next one, and let's see how it's a little different than before. Again, we started just like usual, where I separated the numerator from the denominator. Then, I looked at this first expression, and I saw I have a times the square root of b. That right there is the multiplication. There's no exponent out here, okay? That was different than before. When I had the square root of 2x, that was 2x to the 1/2 power. That's not the same as 2 times root x, okay? Here, the real main operation is the radical. Here, the main first operation is multiplication. So hopefully you're seeing why, let me try to do that a little neater. Hopefully you're seeing why the second step in each problem is a little different. So here I've just separated the a and the root b, and then the square root of b is really, if you remember from working with radicals, that's just b to the 1/2 power. So that's why I moved the 1/2 out front, and we're left with this final expression. And then I also said, by the way, log 5 of 25, I can figure out what that is. It's just a 2. So double check when you have logs of numbers, see if they work, if you can actually get a whole number answer for them. Here, log 3 of 4, well, I can't get a whole number answer for that. 3 to what power gets me 4? Nah, that's not going to work. So just double check to make sure if you can simplify any of them down to whole numbers. But this is going to be our final answer here. Again, hopefully it's making sense to you. And hopefully you're seeing the difference between these two problems in where the root lied, or where the root was occurring. Now let's take a look at this one where I have the entire argument in a root. So here, the argument is the cube root of 7x to the 5th over 2. Well, before I do anything, right, because I want to get the 7, the x, and the 2 by themselves. That's my goal. I want to separate this logarithm so each one of these is their own argument. Before I can even do that, I have to address this cube root. I got to take care of this cube root somehow, because I can't get at the 7, the x, or the 2 when they're inside the radical. So how can I get rid of the radical? Well, again, it's helpful to think about this in terms of exponents. Instead of the cube root, remember this is the same thing as taking 7x to the 5th over 2 to the 1/3 power. The cube root is the same as the 1/3 power. So, knowing that, I can move this out front. So let's move that 1/3 out to the front, and we still have log base 2 of 7x to the 5th over 2. Now, before I can start working with things individually, I better split up numerator and the denominator. So 1/3, I'm going to split it up into log base 2 of 7x to the 5th minus log base 2 of 2. Watch what I'm going to do right here. I'm going to put parentheses all around this, okay? This is saying 1/3 times this whole thing. So when I simplify this to here, I would still have to distribute the 1/3 through to everything, okay? That's why I'm keeping things in parentheses. Now, I can still break this apart. Log base 2 of, well, I have 7 times x to the 5th, so that's log of 7 plus log base 2 of x to the 5th minus log base 2 of 2. Again, hopefully you're seeing why this is working, why I still need parentheses. Let's go ahead and see if any of these individual logs can break down. Well, first up, log base 2 of 7, right away I know that doesn't break down. 2 to what power gets me 7? Well, that's not going to be a whole number, so I don't need to worry about that. I do have an exponent here that I can bring out front to be 5 log base 2 of x. And minus, well, log base 2 of 2, that's just a 1. So here would be our final answer. You could distribute this if you want to get 1/3 log base 2 of 7 plus 5/3 times log base 2 of x minus 1/3. But that's your call. Either of these would be correct for me. Either of these would be correct expressions. All that we're doing here is we're getting each of the values, whether they're numeric values or variable values, as their own arguments. But to do that, we sometimes have to work with simplifying different quantities down, maybe into whole numbers, right? Hopefully this is making sense to you. What I'd like us to do is apply these ideas to now work in reverse. Now what we're going to want to do is take all of those properties that we've just gone over, but this time condense an expanded form down into a single logarithmic expression. Let's review the process. For all of the individual logarithmic expressions, if the logarithms have a coefficient, apply the power property. If there's a coefficient, meaning a number out front of the logarithm, we said before, oh, that came to us because we had an exponent. So remember, if I had something like log x to the 5, I wrote that as 5 log of x. So if you saw any numbers out front here, you would know, uh-oh, those were exponents. So we could put those back as exponents. Then, using the associative property of addition, reorganize the terms so that all of the logarithms with positive coefficients occur first and negative ones occur after. So group all of the addition on one side and all of the subtraction on the other side. Well, let's go ahead and do that right here. Where are my positive logarithms? Here's a positive one. Here's another positive, log base 3 of 10. And then I'm going to have the negatives after it, log base 3 of 20. Okay, I've done that. Now, use the product property to combine the two groups of logarithms. Well, notice that I'm adding logarithms here. I had that property that said if you're adding logarithms and they're the same base, that's important, they all have to be the same base, you could just multiply their arguments together. So we would have log base 3 of 54 times 10, which is just 540, minus log base 3 of 20. What I'm doing here is I know that with this subtraction, I must have a numerator and a denominator to a fraction. So what I'm trying to do is first combine all of the numerator together, which I just did right here. Then I need to combine the denominator. Well, there was just one term, so that must be the denominator. Now I can use this quotient property to combine the logarithms that are being subtracted. Let me write the answer right over here. I'm going to try to do this in a different color. Log base 3 of 540. Oh gosh, I'm running out of room. Let me see if we can just write it like this. Log base 3 of 540 divided by 20. This is what this expression is saying, okay? We put what needs to be in the denominator in the denominator and what has to be in the numerator in the numerator. And when we did that, we got this expression. Now, we could simplify this even more because I have a feeling 540 and 20 probably divide. So if I grab my calculator and said 540 divided by 20, I would get 27. So I'm really being asked to take log 3 of 27. Wait a minute. Log 3 of 27? Isn't that, I know what that number is. 3 to what power gets me 27? Well, that's just a 3. So that would be my final answer for this. This whole expression equals 3. And I could do that with a calculator. I could do that by converting things into exponents. It would make sense. I'd be able to do that. It's just helpful to be able to also condense things down, simplify them into a single logarithm, and then just simplify that logarithm, okay? Let's try some practice problems. In this situation, again, we have 3 separate logarithms. I see they're separated by addition and subtraction, so that means I'm going to be multiplying the positive things together, and I'm going to be dividing by the negative, so I'm going to end up with a fraction. I also see that there's numbers out front. Anytime I dragged a number out front of the logarithm, that meant it used to be the exponent on the argument. So let's drag them back. Let's drag that 3 back, and the 1/3, and the 2. Let's put them back as exponents. So here we would have log base 5 of x to the 3rd power plus log base 5 of y to the 1/3 power minus log base 5 of z squared. What we're doing here is, well, we knew that these must have been the exponents, and we have that property that says you can drag the exponent out front. You can also go in reverse. You can put it back. So we've gone and we've put them back. Now, let's try to see if we can piece together what fraction we're going to have. Well, first off here, notice that I'm adding these expressions together. So that means I must be multiplying the arguments. And again, this is just going off of what properties I know. And then we can say, well, we're also subtracting quantities. So if I'm subtracting, that means that I must be dividing the arguments. X to the 3rd, y to the, oh, I'm sorry, that was a 1/3 power, not a half. And I'm dividing by the argument z squared. This, and maybe if I rewrote the 1/3 power as the cube root of y, same thing, your call if you want to write it as a root or if you want to write it as an exponent. But these two expressions right here are either of the final answers. All right, you can write the final answer either way. What we've done is we said, well, we knew that before we could start combining, we better put those exponents back in place. And then we said, well, if we were adding together, we must have multiplied the arguments. And if we were subtracting, we must have divided the arguments. Again, we're just using the same properties, just going in different directions. What I'd like you to do right now is really give these practice problems a try in the homework, see if they're making sense to you, and see what parts you're struggling with and what parts you need more help on, okay? Really, it's just the same properties again, one going in one direction and then in reverse. If you have any questions, please let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know if you have any questions or comments or things you'd like me to go over. And until next time, take care.